The next part of the review is the digital primer. This review is an overview then of the digital logic and design. We'll look at the binary logic operations and show that gates that perform these functions. And then finally, the logic gates are put together to form simple digital circuits. Finally, we'll cover some of the logic devices commonly found in microcontroller interfacing. And all of these things will be used throughout the course in one shape or another. You'll be required to recall these functions and these logic devices and logic functions when you are doing the assembly coding that we're going to learn as we progress through the course. So we'll be looking at binary logic operations, logic gates, the associated digital circuits for the logic gates, and then the logic devices as they apply to this introductory part of the microcontroller interfacing. You'll recall that binary logic, 1 and 0, really has a correlation to a physical voltage level. Computers use binary systems because of the two voltage levels can be represented in a 0 and a 1. And you can see that for a logic high, it really is, there's a threshold. In this case, the threshold in this diagram is showing you that anything above 3 volts to 5 volts is considered to be a logic high. So you don't get this analog representation of what's going on. The logic 0 is anything below about a half a volt. So this just gives you a little tangible idea of what the ones and zeros are relating to in and on a physical circuit. You've seen the logic gates, you've done some design work, and you've done some calculations and methodology with the logic gates when you went through your digital logic course. Binary logic gates are simple circuits that take one or more output signal and send it out to become an output signal. And it can be AND gates, OR gates, tri-state buffers. You're going to see a lot of tri-state buffers in the use of the microcontroller. Inverters, exclusive ORs, NAND gates, and NOR gates. So you just need to be refamiliarized with the function, what the annotation, what the math looks like, what the diagrams look like for these devices. We always start with the AND gate. The AND gate represented by that diagram, and the mathematical representation or the logic representation, X equals A and B. And so the idea behind an AND gate is you need two highs to make a high. Any low gives you a low. So the AND gate takes two or more inputs and performs a logic AND on it. And you can see from the table here what the inputs and the outputs look like. Simplest case. The OR gate, any high will give you a high. So in this case, X equals A or B is just telling you that either one of those inputs can be high to give you a high at the output. The tri-state buffer, a buffer does not change the logic level of the input, and it's used to isolate or amplify a signal. You can see there with the tri-state buffer, we've got a control function on there that will allow the device really to be controlled on and off, however you want to think about it. It's a pass-through. It does not change the output from X to Y. The inverter, you can see that bubble on the output. You'll recall the bubble is telling you that whatever came in on X is no longer what it was. It's been inverted. So if it comes in as a 1, it goes out as a 0. If it comes in as a 0, it goes out as a 1. The exclusive OR, basically the exclusive OR says that it will produce a 1 output if one and only one input is a 1. Otherwise, it produces a 0. And it makes a very good comparator circuit. So if you look at the truth table, you can see from the truth table input X and Y, a 0 and a 0 will give you a 0. If it's a 0 and a 1, then by the nature of it being a good comparator will be the point that you get a 1. Otherwise, you get a 1 and a 1 gives you a 0. The NAND gate, a not AND gate, functions like an AND gate with an inverter on the output. And you'll see these diagrams drawn multiple ways. This is probably the easiest way to draw an AND gate. You'll notice that the representation over here says that X is equal to not A and not B. Okay, so again, look at the truth table and determine what the output's supposed to look like. The only time you get a high out is when the inputs are either 0 or any 0. If they're both 1s, is the only time you do not get an output. The logic NOR gate, again, functions like an OR gate with an inverter. In this case, the only way that you can get a high is when both of the inputs are low. Every other case will give you a low at the output. Looking at using those gates then as a design function, in this case we look at a half adder. A half adder is a simple logic designed to add two binary digits. We're summing 1 plus 1 and we get a yield of a 0, and then we get a carry. So you think back to the math that we covered in the previous sections. This is how, with the logic gates, we get our carry functions. So using the half adder, using an exclusive OR and an AND gate, or a half adder using an AND and an OR and an inverter. There's lots of ways to come up with values and not values, but designs for a lot of these circuits. Sometimes it comes down to what have you got on hand to make a particular circuit if you're doing the design. Other times it has to do with the characteristics of the circuit. Delay has become very important in these types of circuits, and you might find that one design will work better than the other to get rid of a delay, or to put a delay if you want one in the circuit. Half adders can be simplified by a simple block diagram here. So everything that you saw in the previous circuit is stuffed into that little box, okay, the black box if you want to think about it. You're adding a value X and Y, it goes into the black box. It either comes out on one leg for a sum or the other leg for a carry. It just simplifies looking at the logic if you don't care about the way the circuit was designed, the logic circuit was designed. A full adder, basically two half adders. They're combined to form the half adder. The best way to understand this and look at it is to look at the relevant truth table. So you can see your inputs X and Y and your carry. You can go through and trace this through with zeros and ones and zeros to verify what the outputs are at any of the inputs of the carries, and then verify what happens at the sum when you are adding these values together. Again, ultimately your output becomes a sum and a carry. Again, representing it as two black boxes, two half adders that have X and Y in and a carry function. The carry functions then are output to an OR gate, and they become your final carry and your final sum. Adding 3 bits, if you're looking for a 3-bit solution, then 3 half adders added together. So it's just a matter of stringing the carries from one to the other and looking for least significant bit to most significant bit. Decoders are used widely as address decoding. And you can see on the left here, you've got a couple of inverters input to an AND gate. That is a address decoder for 9, again the binary 1001. the output of an AND gate will be 1 if and only if the input binary is 1001. On the one on the right, the address decoder for a 5, binary 0101. The output of the AND will be a 1 only if the input is 0101. So it really comes down to knowing what your inputs are to get the output that you're looking for. If you're looking for a 1 and you know that the inputs are going to be a certain binary number, you design the circuit to match that number of inputs and outputs. Flip-flops you've probably seen in a couple of your classes. You've at least seen it in your design logic. The flip-flop is frequently used to store data. A D flip-flop is called a latched or a hold type flip-flop. The D flip-flop holds the data as long as the power is on. Okay, so again, diagrammatically as a circuit, you can see it's a bunch of NAND gates tied together, one inverter on the lower NAND gate to give you your output of Q or not Q. Okay, and your Q or not Q value is going to be a 0 or a 1. Simplified diagrammatically, you normally see the little representation in the block diagram B of a D flip-flop. Okay, and then as with any logic device, you have a truth table that's used to identify very quickly what the output is for a series of inputs. Okay, so that is a really quick primer on digital devices and digital logic. The best thing to do is work some problems. Go back, pull out your digital book. I've provided some problems, in the assessments that'll give you a quick brush up. So the next section will be looking inside the computer, refamiliarizing ourselves with the computer architecture.